All right, so on page 6, I'm going to actually tell you that what you just did on that sheet of paper, whether you liked it or not, you'll never do that again. That's the formal definition of the derivative. And tomorrow we start doing it the easy peasy way. So that, actually, that was one of the harder lessons. They're going to be pretty straightforward from here on out. It's just going to be how do I take a derivative without doing that. So I want to show you how AP tests this concept, and so will I. All right? All you really need to do is recognize the format. So I'm going to show you, and we'll come back to this before the next test just to make sure. It's going to seem a little weird right here. But when you, this chapter, by the way, is on derivatives. Had this been last chapter, you would have plugged the 0 in and said, oh, I've got 0 over 0. I've got a problem. I need to multiply by the conjugate and all that stuff. But that's not what it's saying. It's saying that the limits below represent the, whoa! Oh, I forget I'm recording sometimes. Sorry, guys. I just went, whoa, in their ear. So it says this represents the derivative, I don't know why that's not working, for some function f at a specific spot. So this is what you would have done yesterday and how you would have started when you were given a specific function. So sometimes all they do is want to know that you've been taught how to do it the long way and you can pick it apart, which is sometimes harder than doing it itself. But you're supposed to recognize, okay, this is the derivative. How do I know? They told me, right? And I know my format for the derivative, what you guys used yesterday on those 5 problems, is this. And you would stick the x plus h into the f function, correct? Right, Andy? Yes? Yes? You can speak, people. Why is that not? Come on, activate. Maybe that'll go for me. Oh, yay. So you would take the x plus h when you did the whole thing by yourself, and you would put it into the function. That's already been done. So this x plus h got put into a function. Can you see it? So what's the x value that we're doing the derivative at? I shouldn't end in a preposition. At what x value are we doing the derivative? You can see it. None. Correct? So you would just say, well, the c value, or the x, is equal to 9 in this case. You can just see it. They must have put a 9 in for it. It also says to find the function itself. So had this been a function f of x, and you stuck a 9 plus h into it, the function you stuck the 9 plus h into is the square root of x. You're picking it apart, not actually doing it. So these are the 2 things you need to recognize. What was the function? It was a square root function. What do I put into it? X plus h. Well, they put a 9 plus h into it, so x must be 9. Who knows where this 3 is coming from? Go ahead and take a peek. Where's that 3 coming from? Go ahead, tell me, guys. F of x. And f of x is a square root function, and they're doing it at 9. See what I mean? So you just have to pick it apart. And we'll discuss this later. I don't want to spend a ton of time on this, but I want you to know you won't be doing the derivative by hand anymore. It'll kind of be halfway done, and you'll be picking from multiple choice, because the AP exam is multiple choice, what the function is and at which x value. So remember, let's go take a look at this one. This is how you guys started yesterday, right? And you took a limit as h approaches 0. And I told you in the notes, some books use a delta f. So I like the h, so I'm just going to go like that. So x plus h got plugged into a function. So what you do is you go locate an x plus h. All right, so I'm going to go, why is that doing that again? No. All right, so I'm going to go locate an x plus h. Do you see it somewhere up here? I see it. Do you see it? In your nodding person. It's right here, correct? There it is. What's happening to it? It's being cubed, and 2 is being added to it. That's your function. Your original function must have been 2 plus x cubed, and you stuck negative 3 plus h into it. What's your x value for this one? At what point will you be calculating the derivative? What's the x? Negative 3. Yeah. So your C value or your X is negative 3. We're not going to do this one. We'll circle back to that at another time. This isn't the point of today. I just wanted to tell you that you won't have to do it by hand anymore. We're going to talk about 3 instances in which a derivative does not exist. So write this up here. 3 cases where f prime at C does not exist, or you can't take a derivative. All right, remember a derivative's a slope, right? And it's the slope of a tangent line to a function. So this says to sketch the graph and find the derivative of this function. So you should know what that looks like, right? Tristan, what does the absolute value graph look like? It looks like a V. Yeah. At 2, it'd be at 0. At 3, we'd be up at 1. At 4, we'd be up at 2. Right? And at 1, we'd be absolute value of negative 1. So it's actually really 2 lines that get pieced together. Wouldn't you agree? This guy and that guy. But he's right, it does look like a V. It says sketch the graph and find the derivative. So let's write f prime of 2 equals. And if I were to tell Tyler to come up here and draw the tangent line at 2, he's going to go, well, had that been smooth, I know I just go like that because they're approaching 0 from both sides. But this is a negative 1, right? So what's the slope over here? So is the slope of the tangent line negative 1 or 1? And you say, well, I can't tell. It's a sharp corner, right? So we'd say f prime of x does not exist there. Now, got to be careful. If it says to explain is a weak prompt. It can be done in words. Like explain yourself, you use words, correct? So you can just say there's a sharp corner or sharp turn at x equals 2. So on an AP exam, it might say this. It might say, find the places at which the derivative does not exist, explain. And we would say, well, it doesn't exist at x equals 2 because of the sharp turn. Another word for this is called a cusp. AP accepts both of them. Okay, so they accept both for an explanation. But if it says to justify requires mathematical reasoning. It's the thing that's causing the sharp turn versus the smooth turn. Watch this. I'm going to make a smooth turn, and I'm going to have you talk about slopes of tangent lines. Are you ready? I'm going to come in at, let's call this C from the left. So the slope is super negative, right? Right? And then, Joel, it's less negative, right? And I'm drawing these tangent lines, less negative, less negative. It's approaching what slope from the left? 0, right? Tristan, I heard you say it. From the right, very steep down, uphill, less steep, also approaching what slope? 0. The slopes are approaching 0 from both sides, which is causing this smooth turn. For mine, when we approach from both sides, we discuss limits as x approaches 2 from the left. Not of the function, because the limit exists. As you travel in at 2 from the left and at 2 from the right, you are at 0. This is about the slopes. So you're going to go like this. You're telling me that the slope to the left is negative 1, and it is not equaling the limit as x approaches 2 from the right. So let's go up here. What number could I replace this with? If you know how to read the calculus, that's a really easy question, right? What number can I replace this with? What's the slope as I come in from the left, no matter how far? Negative 1, right? And on the right, what's the slope? What's the slope on the right? 8. Yep, 1. That is justified. This math is causing the sharp turn. Sharp turns can also kind of look like this, too. Let's point at that. That's called a cusp or a sharp turn. The slopes are going up, 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 and then they go down, down, down. They're not approaching the same number. It causes a very sharp turn. All right, so that's the first case where a derivative does not exist, is when there's a sharp turn on the graph. Or you can call it a what? Cusp. AP has a whole bunch of things they accept and things they don't. I was grading a paper once, and it wasn't mine. But when you grade, we're at a table with a bunch of people. If you're not sure whether you should accept something, you ask. So somebody said, it was this on the graph, and a student somewhere across the world, we don't know where they come from or their names, wrote shark fin as their explain. No, because it makes a shark fin. Was that accepted? No. Was sharp turn? What do you think? Yes. Sharp corner? Yes. Cusp? Yes. Somebody else wrote doink point. And it was several. So there's some teacher out there in the world that's calling this right here a doink point. That's their own terminology for that. There's no such thing as a doink point, but that's what they called it so their kids could recognize it, which is fine, but you can't write that. So know what? 2 things you can write. Sharp turn or what? Or sharp corner, or let's make it 3. Cusp. Those are accepted. Don't make up your own thing or what it looks like. Yeah, it kind of looks like a shark fin, but that's not what you're going to call it. All right, the second place where a derivative doesn't exist. So let's call this one number 2. The other one, there's 3 instances you're going to look for. We're off to number 2. In algebra 2, like when I have this graph, oh, sorry, my eye is super itchy. I just like scratching it. When I have this graph over here and I go to try to draw the tangent line, if you were to picture, like if I were to say, Ashley, I want you to walk up this hill, she'd go, oh, I'm falling off that cliff right there, right? Because it's going completely straight up. If only for an instant, she still falls off. Wouldn't you agree? That's called a vertical tangent line at C, and your algebra 2 teachers should have said the slope is undefined, right? What that means is when you see a vertical tangent line, you say the derivative doesn't exist. Are you ready? So here's an example of that. The cubed root of x. So let's write f of x equals the cubed root of x. This is a classic graph that has a vertical tangent line. The cubed root of 0 is 0. Cubed root of 1 is 1. The next one I know nice is over 8. Its cubed root is 2. The negative side is really similar, right? Cubed root of negative 8 is negative 2, so it's like this. If you were to graph it on your graphing calculator, it comes in like this, and it goes like that. And we say that it's not differentiable right here. It actually goes a little steeper like it. It's hard for me to draw like that in red. For an instant, it's vertical at that point. So if you see a graph like this, and it asks you to find the derivative at C, what are you going to say? What are you going to say? Doesn't exist. Now, if the C is over here, the derivative does exist. So you got to watch where they put the C. That happened on one of the homework questions. It went like, I think it went like this. But the C, it was a graph like this on your homework. The C is right here. And it asks if the function's continuous at C. Yes. Differentiable at C. Yes. It's smooth, right? Why do you think I was walking around the room and saw a bunch that said not differentiable? They saw what? Sharp turn, but not at C. So be careful with that. So watch it closely. All right, moving on. So here's our first two reasons. Number 1, if there's any kind of sharp turn at that point. So suppose we're rolling around, and then at C, we went, whoa! We're not differentiable there. Or in red, maybe there was an upside down, absolute value is my favorite real world graph, or that I can actually grab a function for that's not differentiable at the vertex. By the way, is this function in red continuous? Yes or no? Keep that in mind. Okay, just for like 5 minutes. Just keep that red one in mind. Reason number 2, vertical tangents. So when you go out, and just for an instant. So those are 2 situations where the derivative does not exist. Situation number 3. We are cruising. So number 3. A function being differentiable means it must have been continuous. If a function is differentiable, then it's not continuous. Sorry, then it is continuous. I was thinking of something else I'm going to talk about in a second. In geometry right now, we're dealing with these statements. I don't know if you guys remember geometry. Do you remember converse, inverse, contrapositive, and all those if-thens from geometry? And the P's and the Q's and stuff? The original one would be called differentiability implies continuity. This is a true statement. Go ahead and write that. If a function's differentiable, then it is continuous. Its converse, continuity implies differentiability, would be if a function's continuous, then it's differentiable. That is false. Go back to that red graph. And I said, is it continuous? Yes or no? The red one. Yes. Is it differentiable at C? No. So that's a perfect counterexample to that. So let's answer this down here first. It says if the converse is not true, which just swaps, the converse would be this. If continuous, then differentiable. If you don't mind if I just abbreviate, I'm not teaching geometry, so I can write that out. A perfect counterexample for that would be anything with a sharp turn like that where you don't lift your pencil. Oops, I should have done it at C. Sorry, that's a bad example. Let's do this guy. Whoop. Whoop. That function is continuous but not differentiable at C. So is that one. Continuous but not differentiable at C. Here's an interesting fact. If you are if you have COVID, then you can't come to school. Is that a true statement? Yes, right? If you don't come to school, then you have COVID. Is that a true statement? No. When you do what's called the contrapositive or swap it, if the original is true, that one's also true. So listen to this one. If you, that's such a bad example, it's too many words. What I'm trying to say is this. If a function's not continuous, then it's definitely not differentiable. This little squiggle means not. So let's write that down just so you know. You're looking, if not continuous at C. Let's make sure that's true. Then not differentiable. I'm going to put some examples. You don't have to draw them, but just so for your homework you kind of know, because it's going to ask you some questions about continuity and differentiability. This right here, not differentiable at C, because it's not continuous. Correct? This guy right here, even though there's a solid dot there, and if I erase this, you don't need to draw him, that guy is not differentiable at C. Why not? It's not continuous. If I say to Joel, hey, Joel, come up and draw the tangent line at C, you'd be going, what? There's a big gap there, right? You can't draw a tangent line at a discontinuity. And what's a derivative? Slope of a what? Tangent line. Yeah, so discontinuities, throw that out. All right, moving on to our last part here. So, when you're estimating the derivative of a graph from a table, okay, this is a really important word. It means, Tristan, you cannot get it exact. You're going to estimate it from a table. So what this graph is doing is charting the temperature of a polar bear in degrees Fahrenheit on a very, very cold day. The temperature's going down. I'm just going to make a fake graph of it, but it's kind of like at 98, and then it goes here, and then I suppose it goes down a little farther, and then here, here, and here, whatever. If that's some function like that, you're supposed to estimate t prime, the derivative, the slope of the tangent line at 5.5 minutes. And you go along here and you go, but 5.5 isn't even on my table. The very best way, go ahead and let's draw like a really fake graph. The very best way to get an estimate for a tangent line when you don't have the actual function. So let's go right here. And if I said, hey, Cage, this black line, I want you to estimate its slope. But you don't know any other points on it. You only know points on the red one. He wouldn't choose this point on the red one and this point on the red one. You can see that that black line slope right here is way off, correct? if he's going to estimate it, wouldn't he try to stay as close as possible to that point? Like, wouldn't he go, well, I got to choose this one. That's much better. So use that concept on the table. You're only going to focus, I call it straddling. You're only going to focus on the two nearest points, and then you're just going to find the slope of the secant line. It's the best thing you can do when you don't have the actual function. You might want to write the word straddle or whatever, but our very best estimate for what that tangent line would be to get right next to it and find the change in temperature, change in y, over the change in time. Does someone have a calculator out real quick? I just, Hannah, did you still have that calculator out? Can you do? Oh, yeah, 90.45 minus 90.73. It's going to be a negative point something. Point what? I thought I heard somebody say it. One more time. Okay, I don't feel like doing it in my head. 2.8? All right. Here's the deal. If Tyler wrote that on my test or the AP test, this is very common, part A to tabular FRQ, you wouldn't get both points. Tell me why. Let's go ahead and read the whole thing. He's like, yep, I know to straddle it. Yep, change in temperature. Yeah, what is it? Units. Okay, so you have to do the units on the top, which is degrees Fahrenheit, per unit on the bottom, which is minutes. So watch that. So if you're watching the video, my minutes got cut off, so it should say per minute, not per meter. Anyway, I want you to cross this off because I don't like you to memorize formulas. If I said to Bella, guess what, to get the equation of a tangent line at c comma f of c, you do y minus f of c equals f prime of c times x minus c. She'd be going, what? Wouldn't you? Like, what is that? We don't do formulas, Carissa, but from Algebra 2, if you know a point on a line and the slope on the line, how did your Algebra 2 teacher tell you to write the equation for the line? It's in point slope form. Do you remember, Ashley, what you would write? Y, yep, is equal to, yep, times, minus, yes. It's called point slope form. Agreed? That's what I want you to use. I don't want you to think of the C's and F of C's, but what I do want you to think about is we're going to write it as y minus the y you know, which in that one was a 3, right, is equal to the slope. But in calculus, what's our slope? The derivative, right? So you're going to write f prime is the slope times x minus the x you know. You're just going to use point slope form, and it's going to be super easy. So then you don't have to memorize a formula. So watch here. It's well, first, this just says find f prime at 4. You just need to know, Avery, that f prime of 4 means the derivative there, or the slope at x equals 4. So this is the graph of f. I go to 4. I need the slope there. That's not calculus. What's the slope of that line? Everywhere on that line. You can do it in your head, right? What is it, Mandy? Ooh, careful. Change in y over change in x. Change in y. 13 minus 1 is 12. Over 6 minus 0 is 2. Excellent. I'm trying to wake you up, sunshine. Even if they said right here, you'd say 2. Right here, you would say 2. Right here, you would say 2. If they said find f prime of 10, then you have to find the slope of that line. Are we good with that? So last one of the day, and then you'll finish in class today. Oops, I have this up from yesterday. I actually think we're going to wait on this. Let's go ahead and write wait. I'm going to cover these two at the beginning of the hour tomorrow. So I'm going to stop this, and I'm going to pass out the worksheet. So now it's activating this. Now when I don't want it to, I'm not flipping you off, by the way. I told you that. I like to use that finger. when I use my highlighter. All right, so on your worksheet, did you guys grab